Okay, let's dive into still tension elements for a little bit. A couple examples. Actually, this one here is from a bridge crane on the Great Lakes. It's the bottom chord. It's the old I-bar system. There's some pretty spectacular failures in the history of these types of members, and this one actually joined that club. Here's a simple brace configuration in an airport hangar out in Wendover. And this is a railway bridge out in St. Louis area. This bottom chord here would be in tension, and then some of the diagonal members, depending on the loading, would also be in tension. I found a little video for you of a tension test just to give you kind of a visual. There's maybe this is something that we'll do in the lab here. I'm not sure how that works with the materials class. And then this picture here shows three different tension specimens. These both have a lot of yielding. You can see how the material necks down, which is basically where it's fully yielded and stretching. This is a piece of aluminum that was not very ductile. There are very ductile aluminums, so this isn't representative of all aluminums. But you can see it didn't have much yield at all. There wasn't much any necking, maybe a teeny bit right here before it ruptured. So this behavior where it can stretch for quite a ways versus this where it's loaded, it reaches its ultimate strength and ruptures can have very different practical effects on structural behavior. All right, under tension, when we pull on a piece of material, the material elongates. So these were originally circles. When I pulled on it, they turned into ovals. Kind of looking at uniform tension stress. If we have a cable that we're pulling on, we cut it, take a look at it, we'll have uniform stress across the entire thing. And if we go back to mechanics of materials, this stress would be equal to the tension force divided by the cross-sectional area. Okay, AISC generally ignores stress increases around the hull, other than to say we have a reduced cross-sectional area. But in reality, there's a stress concentration when load flows around a hull. For fatigue and fracture, we will need to consider that more carefully. For yielding of the gross section, it doesn't matter, but net rupture at the hull, there's a different equation for it, although they end up being similar between net rupture and tension yielding. All right, there's some slenderness recommendations in the code. There's no limit, but they do recommend that the slenderness, so the length divided by radius of gyration, is less than 300. That gives some improved, basically a reduction in sag and then reduction in vibration. All right, phi factors are here. So for yielding, this would be for the gross cross section, 0.9, for rupture, 0.75. And then the basic two equations. So for tension yielding, the strength, the cross-sectional strength, the tension strength of the member is the yield strength times the gross area. And for tension rupture, which would be through any place with a reduced net or reduced cross-section due to holes, would be the ultimate strength times the effective area. And we'll jump into the effective area really quick. It's going to be the net area times a shear lag factor. So this net area, we just calculated basically gross area minus areas the holes made. There's a little discussion here about that. We're going to actually add a 1/16 of the hole, or to the hole size, which accounts for some kind of imperfections in the hole. When you punch holes or you drill holes, they're not always perfect. Sometimes there's gouges or nicks. So that's where that 1/16 comes from. So Shear lag factor, you can go to table D 3.1 on the code. It'll basically give you what it is for different configurations. So if you have a member where all the tension is running through each portion of the member, so like let's say the flange, the web, and the bottom flange were all connected, that would be a shear lag factor of 1. So basically what we're talking about with shear lag is if we connect a flange, like let me go to a bigger image here. So let's say we connected this flange, but the force was applied in the web. There would be a lag due to basically the force transferring from the web into the flange, and so that's shear lag. And basically it creates a stress concentration. So that's what this shear lag factor is trying to account for in kind of a backwards way. Anyway, so depending on the geometry of your connection, you can come in here, calculate the shear lag factor, and apply that to your rupture capacity, which comes up in your effective area calculation. Okay, so a little more on shear lag here, basically expounding on this table with some of the definitions. One of the most helpful things in the manual are their design tables. This is a snip of the axial tension strength table. So say I had a 14 by 30 and I wanted to know what its yielding and rupture strengths were, I could come in here and pick that up. It's important when you're using these rupture values to make sure you understand the assumptions on how much hole or reduction in cross-section there is. Sometimes it's better just to calculate this by hand so you know you've got it dialed in. But it is nice for preliminary design or even final design if you are clear on the relationship of the reduction in cross-section in the table here. Similar table for angles. Very helpful when you're doing just simple bracing design. Couple drawing examples. So here's an elevation view of a simple manufacturing type building. So these are tension only braces. They're called out as angle 4x4 by 3/8. Pretty simple. Here's a more heavy type connection. So this is a cantilevered portion of a building. This brace is in tension. It's a W10 by 60. Let's see, that first brace, that lighter brace would have a connection kind of like this, down to the base plate like that. That other building had connections more like this, substantially heavier, because we're connecting substantially for more force, essentially. Okay, I think that wraps it up. These drawings are intended to help you understand kind of the style and how to show things. Other things I've given you, there's an example here that walks you through tension design, and should be helpful to you here. And then finally, just as a reminder, there are some example drawings here in the course basics and resources, example calcs and drawings. You can come in here and have a full set of that shop that I showed you and some of the other snips that I have in there. This has general notes, foundation plan, plan views, so this simple still framing. Elevation, so kind of the full picture of that, elevation tags, etc. And then all the details for the project. Not a super complicated project, but good representation of some typical industrial type drawings. Anyway, we'll talk more in class as always, and looking forward to getting more into this together.